Okay, trees are very special sorts of graphs. They're all in one piece, so they're a connected graph, and they have this property that there are no cycles in them. So some examples. I'm not going to label the vertices, I'm just going to draw them. So here's a tree which is basically a path of length 1, 2, 3, 4. Here's another tree. It's almost the opposite of a path. It's a star. Again, 1, 2, 3, 4. This has 5 edges and 1, 2, 3, 4, 5, 6 vertices. Something which sort of shows you why these things are labelled trees. They sort of have a tree sort of shape. Traditionally we draw them a bit like this, but you can see the tree shape if I round it upside down. It's the same object. A very small tree, just a vertex by itself. So all of these, if you think about them, that's connected. It's all in one piece, and obviously you can see that there are no cycles in it. Again, one piece, and again, no cycles. One piece, no cycles. One piece, and no cycles. In fact, there are no edges at all. If we go a little bit further, if we count the number of vertices here, 1, 2, 3, 4, 5 vertices, and how many edges? 1, 2, 3, 4 edges. Here, how many vertices? 1, 2, 3, 4, 5, 6. How many edges? 1, 2, 3, 4, 5. How many vertices in this one? A bit harder to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 if I've done it correctly. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 edges. Here, only old vertex by itself, so one vertex, and how many edges? 0. If you start looking at this, you see a pattern emerging, and the pattern is that in a tree, there's always, the number of edges is always 1 less than the number of vertices, or the number of vertices is 1 more than the number of edges. Usually we talk about the number of edges being 1 less than the number of vertices. So 6 minus 1 is 5, 15 minus 1 is 14, 1 minus 0, 1 minus 1 is in fact 0. Several other properties, I mean that's a very important one, and that's a characteristic. So if I tell you I've got a graph that has a connected graph that has 6 vertices and 5 edges, you know straight away that it must be a tree. That's going to be, that is in fact one of the definitions. There's a whole subject in second year that some of you might like to take called graph theory. The whole subject is about graphs and trees and the various uses that can be made, as well as the various interesting things that happen for them. So there are other sorts of properties of trees. So here's, I'm just going to draw another tree here, and I'm being careful not to put any cycles in it. And what you observe is that if I add an edge between any 2 vertices, say this vertex and this vertex, if I add an edge, I'll go around that way, that automatically creates a cycle in here. So adding an edge creates a cycle. And it turns out that that is another way of characterizing a tree. So if I've got a connected graph, and I can say that whenever I add an edge between 2 existing vertices, so notice I'm not adding an extra vertex, I'm just adding an edge between 2 existing vertices. that's another characteristic or a characterization of a tree. Another characterization is, I'll do this in pencil because I want to erase something. Suppose I take another tree. That, so that goes off there. Let's put another one in for good measure. Another characteristic of a tree is that if I remove an edge, then it breaks it into two pieces. So let's choose an edge. Let's choose this one. If I remove it, what happens? I now have two pieces, two components. It disconnects the graph. So that's another characteristic of trees. Removing an edge disconnects the graph, or results in a disconnected graph. Actually, we should do another one of those just to show you, so you can see that here's one component and here's another component after we've removed that dotted edge. I'll do that again because suppose I've just take a smaller tree like that, and suppose we try and remove this edge. What happens? Okay, we remove that edge, and immediately you see that I end up with two pieces. It's just that one of the pieces has only one vertex in it. So this idea of removing an edge disconnects the graph also applies to an edge that looks like this. The other characteristic that's really important about trees is something I sort of alluded to before. Let's actually put some labels on things. So A to B, C, D, E, something like that. If I choose any two vertices, let's say K and C, there's K and C, you'll see that there's exactly one path that gets you from K to C. So K to I to G to B to A to C. And there's no other way. You can't sort of go off somewhere else and come back again, because if you could do that, you'll actually have a cycle in there. If I want to get from D to J, there's exactly one way of doing that. Going up around there. I can't go off to C and then come down, and there's no way of getting this way. If I want to go from L to M, I've got to go this way, and that's the only way I can do it. So that's another characteristic of trees, that there's exactly one path between each pair of vertices. So, between each pair of, we'll say, distinct vertices, because we don't want to start and end at the same place. There is exactly one path. There aren't two paths, there are no paths. If there were no paths between two particular vertices, you'd have a disconnected graph. If there were two ways of getting, so let's do an example. If you've got two ways of getting from A to D, then you've obviously got to have some sort of cycle. A to D in one direction, an A to D in the other direction, and that forces you to have a cycle. So definitely not a tree. It's also not a tree because if you remove this edge, say B to C, it's still in one piece. So we'll go ahead there, remove the edge B to C, it's still one piece.